Hello, in this lecture we will find the size of line segment AE. In the drawing we have square ABCD. We know that angle BED equals to 90 degrees. This angle equals to 90 degrees. BE equals to 2 units. DE, line segment DE equals to 8 units. And we want to find out the size of line segment AE. So we'll connect together points A and E for set line. So we want to find out the size of line segment AE, the line in the red color. Okay, so first of all we will connect together points B and D by a straight line. Actually, triangle EBD, this triangle is a right triangle because it has one angle that equals to 90 degrees. So I will write it down. Triangle BED is a right triangle. Therefore, we can implement the Pythagoras theorem in the right triangle, triangle BED. Okay. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle BED is side BD in the red color. Therefore, the square of the hypotenuse in the right triangle EBD, it is actually BD square. And BD square equals to the sum of the squares of the perpendiculars equals to EB square plus DE square. So BD square the square of the red line, the hypotenuse, equals to EB square. EB equals to 2 units, so EB square is 2 square, 2 square is 4, plus DE square, DE equals to 8 units, so DE square is 8 square, 8 square is 64. So in total we got that BD square equals to 4 plus 64, that is to say BD square equals to 68. Here we will take a root out of equation number 1 and we will get that PD equals to the square root of 68. So we found out that BD BD, the hypotenuse, equals to the square root of 68 units. BD is also the diagonal of square ABCD. We know that all the angles inside the square are right angles, therefore angle BCD equals to 90 degrees. It is a right angle. And also angle BAD is a right angle. It equals to 90 degrees. So in the next step I will present to you rule number 1. Rule number 1 states that the diagonals of a square bisect or cross the angles of the square into 45 degrees angles. So I will read rule number 1 again. Rule number 1 states that the diagonals of a square bisect the angles of the square into 45 degrees angles. Actually, all the angles inside the square are right angles. So if the diagonals bisect the angles of the square, each angle must be equal to half of 90 degrees. That is actually 45 degrees. So therefore the diagonals of the square bisect the angle of the square into 45 degrees angles. So we have in the drawing diagonal DB of the square ABCD, and according to rule number 1, this diagonal DB bisects angle ADC into 45 degrees. So this angle will be equal to 45 degrees, and this angle ADB will be also equal to 45 degrees. Likewise, angle ABC must be equal to 45 degrees because of the fact that the diagonal DB bisects this angle that equals to 90 degrees. Therefore, this angle must be equal to 45 degrees according to rule number 2. And angle ABD must be also equal to 45 degrees, according to rule number 1. So if we focus on the right triangle DBC, on the right triangle DBC, cosinus 45 degrees equals to DC over DB. And we will define angle, and we will define side DC of square ABCD as y. That is to say, DC equals to y units in its size. So we got that cosinus of 45 degrees equals to DC over dB. But DC equals to y according to our definition. And we have already found out that dB equals to the square root of 68 units. So in total we got that cosinus 45 degrees equals to y over square root of 68. We know that cosinus 45 degrees equals to square root of 2 over 2, so we will substitute cosinus 45 degrees by square root of 2 over 2, and it equals to y over square root of 68. Here we will multiply equation number 2 by square root of 68. And we will get that y equals to the square root of 2 over 2 times square root of 68. According to equation number 2, we know that 68 is 34 times 2, so we substitute 68 inside the root by 34 times 2, and we will get that y equals to square root of 2 over 2, and we substitute 68 by 34 times 2. We have a rule that the square root of a times b, the square root of a times b equals to the square root of a times square root of b. So according to this rule, the square root of 34 times 2 will be equal to the square root of 44 times square root of 2. So I write it down. Square root of 34 times square root of 2 times square root of 2 over 2 equals to y. Square root of 2 times square root of 2 is 2, so I write it down. We got that y equals to 2, 2 over 2 times square root of 34 2 over 2 is 1, so 2 will get cancelled. And we actually found that y equals to square root of 34 units. And we also know that all the sides of a square are equal to each other, so all the sides in square ABCD will be equal to the square root of 34 units. Y equal to the square root of 34 units. BC will be also equal to the square root of 34 units. AB will be also equal to the square root of 34 units. And AD will be also equal to the square root of 34 units, because of the fact that all the sides of a square are equal to each other. So in the next step, I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, if a line segment AB subtends two equal angles, two equal angles, on the same side, then quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. I will read rule number 2 again. Rule number 2 states that if a line segment AB subtends two equal angles on the same side, then quadrilateral ABCD is inscribed by a circle and the 4 points A, B, C and D lie on that circle. So what is the meaning of rule number 2? The meaning of rule number 2 is that if we have line segment AB, okay, we have this line segment AB. Okay, we have this line segment AB, and we also have two equal angles that rest on line segment AB. Okay, so the first angle that rests on line segment AB is this angle ACB, rests on line segment AB, and angle ACB equals to theta, and we have also second angle that also equals to theta, that also rests on the same line segment AB. So actually this angle ADB, that also equals to theta, rests on the same line segment AB. Okay? So if this is the situation, then according to rule number 2, the quadrilateral ABCD, this quadrilateral ABCD, this quadrilateral is inscribed by a circle, and the 4 points A, B, C and D lie on that circle. So quadrilateral ABCD is inscribed by a circle, again, quadrilateral A, B, C, D. This quadrilateral is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. Okay, so I will repeat again on rule number 2. If we have line segment AB, this line segment AB, and we have two equal angles, those two angles are both equal to theta, angle ACB and angle ADB, they are both rest on the same line segment AB. So therefore, according to rule number 2, the quadrilateral ABCD, this quadrilateral is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. Okay, that is actually the explanation of rule number 2. Okay, so we actually arrived to this drawing by implementation of rule number 2. This is the explanation of rule number 2. And then we actually can implement rule number 2 in our drawing. Because we actually have here two right angles. Both those two right angles rest on the same line segment DB in the red color, and therefore, according to rule number 2, the quadrilateral AEBD is inscribed by a circle, and the 4 points AEBD lie on that circle. So, according to rule number 2, the quadrilateral AEBD is inscribed by a circle, and the 4 points AEBD lie on that circle. Why? Because we have two equal angles that rest on the same line segment BD. So I will draw the implementation of rule number 2 in our original drawing. So I repeat again on rule number 2, because of the fact that those two right angles, they are both subtend or rest on the same line segment BD. Therefore, the quadrilateral AEBD is inscribed by a circle, and the 4 points AEBD lie on that circle. So, the quadrilateral in the green color, quadrilateral AEBD is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. So, actually, the quadrilateral in the green color, the quadrilateral AEBD is inscribed by a circle. So I will draw quadrilateral AEBD inside this circle. So as you can see on this drawing, we have quadrilateral AEBD in the green color, that it is inscribed by this blue circle, and we have actually angle BAD, that is a right angle. So I will repeat on rule number 2 again, because of the fact that we have two equal angles. Those two angles are both angle BED is equal to 90 degrees and angle BAD also equals to 90 degrees. Both those two equal angles lie or rest on the same line segment DB. Therefore, according to rule number 2, the quadrilateral AEBD is described by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. So this drawing is the implementation of rule number 2 in our original drawing. So we actually implemented rule number 2 in our original drawing, in this drawing, and we got to this drawing, and this drawing is true according to rule number 2, because of the fact that those two right angles rest on the same line segment BD. Therefore, the quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay? So, in the next step, I will present to you rule number 3, and we will implement rule number 3 in this drawing. We arrive to this drawing by implementation of rule number 2 in the original drawing, in this drawing. So I present to you rule number 3. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. I will repeat on rule number 3 again. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So what is the meaning of rule number 3? The meaning of rule number 3 is that if we have quadrilateral ABCD that is inscribed by a circle, so I will draw quadrilateral ABCD that is blocked by this circle. And you should remember that rule number 3 is valid, is true only when we are talking about quadrilaterals that are inscribed by a circle. Otherwise, it is not true. Okay? So we must have a quadrilateral that is inscribed by a circle. In order to implement rule number 3, we must have quadrilateral that is inscribed by a circle. Okay? So in this drawing, we have quadrilateral ABCD that is inscribed by this blue circle, and quadrilateral ABCD has two diagonals. The first diagonal is diagonal AC, and the size of diagonal AC of quadrilateral ABCD is x units. Diagonal AC equals to x units in its size, and quadrilateral ABCD also has second diagonal, diagonal BD, and the size of diagonal BD is y, that is to say diagonal BD equals to y units in its size. So according to rule number 3, if we have quadrilateral that is inscribed by a circle, like in this drawing, quadrilateral ABCD is inscribed by this blue circle, then according to rule number 3, the product of its diagonals, that is to say x times y, equals to the sum of the products of its opposite sides. So first of all, we will define the size of side DA of quadrilateral ABCD as A. We will also define the size of side DC of quadrilateral ABCD as B. That is to say, the side DC equals to B units in its size. And we will define side BC of quadrilateral ABCD as C. That is to say, BC equals to C units in its size. And we will define side AB of quadrilateral ABCD as D. That is to say, AB equals to D units in its size. So, according to rule number 3, if we have a quadrilateral that is inscribed by a circle, like in this drawing, the product of its diagonals, that is to say x times y, equals to the sum of the products of its opposite sides. Quadrilateral ABCD has two pairs of opposite sides. Side AB is opposite to side DC, this is the first pair of the opposite sides, and also quadrilateral ABCD has second pair of opposite sides. Side AD is opposite to side BC, and the sum of the products of its opposite sides, it is actually the first product of its opposite sides is D times B. And the second product of its opposite sides is A times C. And the sum of products of its opposite sides is DB plus AC. And DB plus AC, that is the sum of the products of its opposite sides, equals to the product of its diagonals, that is to say x times y. The product of its diagonals is x times y, and x times y equals to the sum of the products of its opposite sides, that is actually dB plus AC. The first product of its opposite sides is B times D. The second product of its opposite sides is A times C. And the sum of the product of its opposite sides is dB plus AC. And that sum of the product of its opposite sides equals to the product of its diagonals, that is to say to x times y. Okay, so whenever you have quadrilateral that is inscribed by a circle, we know that the product of its diagonals, x times y, equals to the sum of the products of its opposite sides, that is to say BD plus AC. Okay, so that is actually rule number 3. Okay, that is the explanation of rule number 3. And we will implement rule number 3 in our drawing. I repeat again, we arrived to this drawing by implementation of rule number 2 in the original drawing. In this original drawing, we implemented rule number 2 in this original drawing, and we arrived to this drawing. Now we will implement rule number 3 in this drawing. First of all, we can implement rule number 3 in this drawing because of the fact that we have quadrilateral AEBD that is inscribed by this blue circle. Therefore, we can implement rule number 3 in this drawing. Whenever you have quadrilateral that is inscribed by a circle like in this drawing, you can implement rule number 3. And according to rule number 3, the product of quadrilateral AEBD diagonals, it is actually AB times DE. The product of quadrilateral AEBD diagonals is AP times DE. Diagonal AB times diagonal DE, and that product AB times DE equals to the sum of the products of its opposite sides. The first product of its opposite sides is AE times DB, and the second product of its opposite sides is AD times EB. AD times EB is the second product of its opposite sides. And the sum of the products of its opposite sides is product 1 plus product 2. That is to say AE times BD plus AD times EB. And the sum of the product of its opposite sides, that is actually this expression, equals to the products of its diagonals, that is actually diagonal AB times diagonal DE. Okay, so actually that is the implementation here. Equation number 3 is the implementation of rule number 3 in our drawing. Again, equation three is equation 3. This equation is the implementation of rule number 3 in our drawing. Okay? And the reason that we can implement rule number 3 in our drawing is because of the fact that we have quadrilateral AEBD that is described by the blue circle. Okay? So the only thing that is left to do is to put the data inside equation number 3 in order to find the size of line segment AE that we are looking for. Okay? So I will copy again equation number 3 and we will find out the values of all the variables inside the equation number 3 for the drawing, and in this way we will find out the value of the missing line segment AE that we are looking for. So according to equation number 3, AB times DE equals to AE times DB plus AD times AB. Okay, so what is the value of AB? The value of AB is actually AB equals to the square root of 34. What is the value of DE? DE equals to 8 units according to what is given us the question. Okay. AB equals to the square root of 34, DE equals to 8, and all equals AE is the missing line segment, so we will leave it as it is. Times dB. What is the value of dB? The value of dB is square root of 68 units. So here we found out that AE is AE and dB equals to the square root of 68 units. And what is the value of AD? AD equals to square root of 34 units. And EB equals to 2 units. Okay, here AD equals to the square root of 34 units and EB equals to 2 units. So here we have square root of 68. Square root of 68. 68 is 34 times 2. So we will write it down. And we will not change the other variables. We will leave them as they are. We will only change 68 to 34 times 2. So 68 is 34 times 2 plus square root of 34 times 2. I've already showed you that the square root of A times B equals to the square root of A times square root of B. Therefore, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2. So I will write it down. Square root of 34 times 2 equals to the square root of 34 times square root of 2. And all the other variables, we will not change them, we will leave them as they are. Here we will divide the equation number 3 by square root of 34. So here square root of 34 will get cancelled. Here also it will be cancelled. So what is left after we cancelled square root of 34? What is left is it is actually eight equals to the square root of 2 times AE plus 2. So that is what is left after we cancel square root of 34. Here we can subtract 2 from equation number 3. And we will get that 8 minus 2 is 6 equals to the square root of 2 times AE Here we will divide the equation number 3 by square root of 2, and we will get that AE, the line segment that we are looking for, equals to 6 over square root of 2. We know that 6 equals to 3 times 2, so we'll substitute 6 by 3 times 2 in equation number 3, and we will get that AE equals to 3 times 2 over square root of 2. So here we will multiply this expression by square root of 2, and then we will divide it by square root of 2, so we change nothing. Therefore it is allowable to do this operation. We will get that AE equals to 3 times 2 over square root of 2, and we will multiply this expression by square root of 2, and then we will divide it by square root of 2. So here we have in the denominator square root of 2 times square root of 2 is 2. So I write it down that AE equals to 3 times 2 times square root of 2. Square root of 2 times square root of 2 is 2. So we got that A equals to 3 times 2 times square root of 2 over 2. 2 over 2 is 1, so 2 will get cancelled. And we actually found out that AE, the line segment that we are looking for, equals to 3 times square root of 2 units we found out that AE, the line segment that we are looking for, equals to 3 times square root of 2 units, or in terms of numbers, AE equals to 4.243 units. Okay, so we actually found out that AE equals to either 3 times square root of 2 units, or in terms of numbers, line segment AE, this line segment, equals to 4.243 units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the size of this line segment AE. We have square ABCD, and we know that angle BED, this angle equals to 90 degrees, line segment EB equals to 2 units, line segment DE equals to 8 units, and we want to find out the size of line segment AE in the red color. Okay. So, first of all, we join together points B and D by a straight line. So, BD in the red color, which is actually the diagonal of quadrilateral ABCD. But by doing this operation, we created triangle EBD. This triangle, it is a right angle because of the fact that angle BED is a right angle. Okay, so actually triangle BED is a right angle, therefore we can implement the Pythagoras theorem in the right triangle, triangle EBD, according to the Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is BD square, and it equals to the square of the sum of the squares of the perpendiculars equals to EB square plus DE square. According to the Pythagoras theorem, in the right triangle, triangle BED, BD square equals to EB square plus DE square. But we know that EB equals to 2 units, so EB square is 2 square, 2 square is 4. And we also know it is given us the question that DE equals to 8 units, so DE square is 8 square, 8 square is 64. 4 plus 64 is 68, so we got that DB square equals to 68. We took a root out of equation number 1 and we found out that DB equals to the square root of 68 units. So this DB, that is also the diagonal of square ABCD, equals to the square root of 68 units. Okay, and then I presented to you rule number 1. According to rule number 1, the diagonals of a square bisects the angles of the square into 45 degrees angles. So all the 4 angles inside the square are right angles, and the diagonals bisect them. That is to say, they create angles of 45 degrees. So we have diagonal DB bisects the 2 right angles. That is to say, this angle will be equal to 45 degrees and this angle will be also equal to 45 degrees. Likewise, here the diagonal DB bisects angle ABC. That is to say, it creates 2 angles that are both equal to 45 degrees. This angle will be equal to 45 degrees and this angle will be also equal to 45 degrees. So we know that triangle DBC is a right triangle, therefore cosinus 45 degrees equals to DC over DB. Cosinus 45 degrees in the right triangle, triangle DBC equals to DC over DB. We defined DC as y, so we substituted DC as y, and we have already found out that DB equals to the square root of 68 units. So in total we found out that cosinus 45 degrees equals to y over square root of 68 units, and we also know that cosinus 45 degrees equals to the square root of 2 over 2. So we substituted cosinus 45 degrees by square root of 2 over 2, and then we multiplied this equation number 2 by square root of 68, and we got equation number 2 that states that y equals to the square root of 2 over 2 times square root of 68. 68 equals to 34 times 2. So we substitute 68 here by 34 times 2. And we have the rule that says that square root of a times b equals to the square root of a times square root of b. So according to this rule, the square root of 34 times 2 will be equal to the square root of 44 times square root of 2. Okay, so we substituted square root of 44 times 2 by square root of 34 times square root of 2 according to this rule. And we got this equation. We know that square root of 2 times square root of 2 is 2. So we have the equality that states that y equals to 2 over 2 times square root of 34. 2 over 2 is 1, so 2 will get cancelled, and we found out that y equals to the square root of 34 units. So, and we also know that all the four sides of a square are equal to each other. Therefore, if this equals to the square root of 34, then all the other sides will be equal to square root of 34. Then I presented to you rule number 2. According to rule number 2, if a line segment AB subtends two equal angles on the same side, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So, what is the explanation of rule number 2? The explanation of rule number 2 is that if you have line segment AB, so we start with line segment AB, only without any other things. And we have also those two equal angles that subtend or rest on the same line segment AB. This angle ADB, rests on line segment AB, and this angle ACB also rests on line segment AB. So we have two equal angles that rest on the same line segment AB. Therefore, according to rule number 2, the quadrilateral ABCD, this quadrilateral, is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. Okay, this is the explanation of rule number 2. Whenever you have a line segment and two equal angles that rest on that line segment, then actually the quadrilateral that is created by the two angles and the line segment is inscribed by a circle, and the 4 points lie on that circle. Okay, and we actually implemented rule number 2 in our drawing. Actually, we can implement rule number 2 in our drawing, because in our drawing we have those two right angles. They are both rest on the same segment line DB in the red color. Therefore, according to rule number 2, because of the fact that we have two equal angles that are both rest on the same line segment DB, therefore the quadrilateral AEBD is inscribed by a circle, and the 4 points AEBD lie on that circle. I repeat again, we have line segment BD, and we have two equal angles. Those two angles are both right angles. Angle BD equals to 90 degrees, and it rests on line segment BD. Angle BAD also equals to 90 degrees, and this angle also rests on line segment BD. So we have two equal angles. They are both right angles, and they rest on the same line segment BD. Therefore, according to rule number 2, the quadrilateral in the green color, quadrilateral AEBD, is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, so actually this is the implementation of rule number 2 in our drawing. Okay, then I presented to you rule number 3, and we also implemented rule number 3 in this drawing. Rule number 3 states that if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So what is the meaning of rule number 3? The meaning of rule number 3 is that if you have quadrilateral ABCD, this quadrilateral in the red color that is inscribed by this blue circle, So whenever you have quadrilateral that is inscribed by a circle, you can implement rule number 3. And according to rule number 3, whenever you have quadrilateral that is inscribed by a circle, then the product of its diagonals, that is to say x times y, equals to the sum of the products of its opposite sides. I will repeat again, quadrilateral ABCD has two pairs of opposite sides. Side AD is opposite to side BC and side AB is opposite to side DC. So the product of those two opposite sides is A times C here, and the product of those two opposite sides is B times D, and the sum of the product of the opposite sides is B times D plus A times C. And that sum of the product of its opposite sides equals to the product of its diagonals, that is actually x times y. I'll repeat again, the product of its diagonals, that is x times y, equals to the sum of the products of its opposite sides, that is actually BD plus AC. Okay? That is the explanation of rule number 3, and we actually implemented rule number 3 in our drawing. First of all, because of the fact that we have quadrilateral AEBD in the green color that is inscribed by a circle, we can implement in this drawing rule number 3. Whenever you have quadrilateral that is inscribed by a circle, you can implement rule number 3. Okay? So, according to rule number 3, the product of quadrilateral AEBD diagonals is AB times ED or DE. Okay, AB times DE is the product of its diagonals. The product of its diagonals, the product of the green quadrilateral diagonals is AB times DE. We have diagonal AB and diagonal DE, and the product of those two triangles, the product of those two diagonals is AB times DE, and that product equals to the sum of this product of its opposite sides. So the first product of its opposite sides is AE times DB, AE times DB, and the second product of its opposite sides is AD times BE, AD times BE, and the sum of the product of its opposite sides is product 1 plus product 2. Okay? And the sum of the product of its opposite sides equals to the product of its diagonals, that is actually AB times DE. So equation number 3 is the implementation of rule number 3 in our drawing. Okay? And I copied equation number 3 here, and we know that AB equals to the square root of 34, DE equals to 8, AE is the missing line segment, DB equals to the square root of 68, AD equals to the square root of 34, and BE equals to 2 units. Here we substituted 68 by 34 times 2, because 34 times 2 equals to 68, and we don't change anything else. So we got this equality. Here we divided equation number 3 by square root of 34. So square root of 34 will get cancelled, and after we cancel square root of 34, the expression that is left is actually this expression left after we cancel square root of 34. 8 equals to the square root of 2 times AE plus 2. We subtracted 2 from equation number 3 here. 8 minus 2 is 6. 6 equals to the square root of 2 times AE. We divided equation number 3 by square root of 2, and we got that AE equals to 6 over square root of 2. We know that 6 equals to 3 times 2, so we substitute 6 by 3 times 2. Here we multiplied this expression by square root of 2, and then we divided it by square root of 2, so we change nothing. Okay. And here in the denominator we have square root of 2 times square root of 2 is 2. So in total we got that AE equals to 3 times 2 times square root of 2, and square root of 2 times square root of 2 is 2. And here we divided equation number 3 by 2, and 2 over 2 is 1, so 2 will get cancelled. And we found out that the size of line segment AE is actually equals to either 3 times square root of 2 units. Okay, the size of this line segment AE in the red color equals to either 3 times square root 2 units, or in terms of numbers, the size of line segment AE equals to 4.243 units. I repeat again, the size of this line segment, the line in the red color, equals to either 3 times root 2, 3 times square root 2 units, or in terms of numbers, it equals to 4.243 units. Okay, thank you very much.